My name is Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm the robot doctor. Here's one of my ground robots driving down the hallway. How does it know where it will end up when it tells its wheels to turn? How far does it need to turn each wheel to reach its final position? In Lesson 105, we will explore how ground robots move. We will also look in detail at how to write math equations that reflect the robot's position over time. This episode will be talking a lot about circles and the math equations that go with them. So as always, be prepared to take notes. While all robots need to move, today we will focus on ground robots. But before we start looking at the math, let's look at the possible wheel configurations these robots can have. In general, these can be broken down into three broad categories: omnidirectional, bicycle model, and differential drive. The type of wheel configuration affects how the robot can move. Hey robot, can you draw a circle? The first category is omnidirectional. The robot can point its wheels in any direction and apply power to move. Since the robot simply points in the direction it wants to go and drives in a straight line, the math is pretty straightforward, so we won't spend a lot of time on that today. The next category when we talk about robot wheel configuration is the bicycle model.
Picture yourself on a bicycle. Your bicycle has one wheel that is driven by you via the pedals and another wheel that is turned with your arms. For a robot built using the bicycle model, there are two motors. One of them controls speed, for example, how fast to spin one of the wheels. The other motor steers, controlling the direction of the bicycle. Expanding this further to 4 or even 6 or more wheels also doesn't change anything. In fact, this model is commonly used in self-driving cars.
The third category of wheel configuration is the differential drive. Let's take a closer look.
Instead of having separate motors to control speed and direction, you have one motor driving the wheels on the left side and another motor driving the wheels on the right side. We can control the robot by setting the difference in speeds between the two motors. If both motors are going forward with the same speed, the robot would travel forward in a straight line. If both motors have the same speed but opposite directions, the robot will spin in place. Putting two slightly different forward speeds on each side will result in the robot traveling in a circular arc. The greater the difference in speed, the tighter the turn.
In practical applications, most robots don't simply have two wheels. They usually add a small unpowered caster in the back or multiple wheels or tracks on the sides for stability reasons. That way they don't have to worry about tipping over. Since differential drive robots are very common in the world of robotics, and they're very simple to explain mathematically, we'll explore the motion of this robot type deeper. What we want to know is, what command should we give the robot's motors to move in the direction we want to move? Conversely, the question is, where does the robot move for a given motor command? We call the equations that relate these two questions the equations of motion. Let's start by defining some terms we will use to discuss robot motion. We will call the direction a robot is facing its orientation, or heading, and it is commonly measured with respect to the x-axis. In other words, the robot's orientation, typically annotated with the Greek letter theta, is the angle between the x-axis and the direction the robot is facing. We'll use the subscript r for robot. The second thing we need to discuss is the relationship between how fast something such as a wheel turns with how fast it moves forward. We need this in order to relate our motor speeds with our robot speeds. If we spin a wheel around one time, we know the wheel has rotated 2 pi radians. We also know that we have moved along the ground a distance equal to the circumference of the wheel. Circumference is equal to 2 pi times the radius. Therefore, rotating 2 pi radians will result in traveling 2 pi times the radius in meters. In other words, the distance s traveled by the wheel is equal to the angle theta by which the wheel is rotated times the radius r of the wheel. We'll use the subscript w when we are talking about the wheel. Let's figure out the relationship between the speed that the wheel moves with the speed that the wheel rotates. If we rotate a wheel for a certain length of time, then we can find the distance traveled by the wheel over that same length of time. Distance over time we know is speed, which is also called linear velocity, the speed along a line. In the same way, the number of angles rotated through over time we call the angular velocity. It's the speed of rotation. The angular velocity we refer to with another Greek letter, omega, which looks kind of like a lowercase w. We can equate linear and angular distances as we have shown previously. If we divide both by time, we get a relationship between linear and angular speeds. Angular velocity equals linear velocity divided by radius, or the angular velocity times the radius equals linear velocity. Now let's look at a specific example of determining robot motion. If we command both the left and right wheels, which are r centimeters in radius, to turn forward at omega radians per second, where will the robot be in t seconds? We know we are turning the wheel at omega radians per second. This multiplied by the radius r gives us a linear velocity of omega r. If we keep this velocity up for t seconds, we'll have gone omega rt meters forward. Now that we know how far we have gone, we need to figure out our final position. We can use trigonometry to help out. Let's create a triangle. Our distance traveled we just figured out, omega rt, so that is the hypotenuse. We'll break up our new motion into two components, a displacement along the x-axis and a displacement along the y-axis. Starting with our x displacement, we know that our angle theta is between the x-axis and our robot heading. So the cosine of theta is equal to the adjacent side divided by the hypotenuse. This can be rearranged to be our x displacement equals our total distance times cosine of theta. Likewise, the opposite side of the triangle corresponds to the y displacement and is equal to our total distance times the sine of theta. Therefore, if we start at x, y with orientation theta, and the total displacement we calculated earlier was omega rt, we will end up at time t at x-coordinate of x plus omega rt times the cosine of theta, and a y-coordinate of y plus omega rt times the sine of theta, and the same robot orientation we started with, theta. So we can go straight pretty easily, but what about making curves?
The wheels can't skid. Because of that, when they go around a curve, they must always be tangent to that curve. Think of your bicycle tire. When you make a turn, it always remains tangent to the curve you are going around. Since both wheels are bolted to the same robot, both of them must have the same point they are rotating around. Otherwise, one of them wouldn't be tangent to the curve. When we look at this, we see that both wheels must trace out a circle centered around this common point of rotation.
So now, let's look at how we calculate this radius. If we assume our robot has a width of L, and we want the robot to follow a circle of radius r, then we can see that the inner wheel must trace out a smaller circle of radius r minus L over 2. And the outer wheel must trace out a larger radius at r plus L over 2. From our earlier equation, we know that the angular velocity is equal to the linear velocity divided by the radius. Using the same formula, we can say the right wheel velocity is equal to the robot's angular velocity times the radius of the circle plus L over 2. And the left wheel velocity is equal to the robot's angular velocity times the radius of the circle minus L over 2. Remember that the velocity of the wheel is the angular velocity of the wheel times the radius of the wheel. Subtracting these two equations from each other, we get the robot's angular velocity times L is equal to the right wheel's angular velocity minus the left wheel's angular velocity times the wheel radius. And now we have an equation telling us what our robot's angular velocity is based on our wheel speeds. Since we're now turning our wheels at different speeds, we need to make a slight modification to our original equation for straight line motion. We now will use the average angular velocities for the two wheels. This will become x will be equal to x plus the average angular velocity of the wheels times r times t times the cosine of theta, and y will be y plus the average angular velocity of the wheels times r times t times sine of theta, where the average angular velocity is the angular velocity of the right wheel plus the angular velocity of the left wheel divided by 2. However, since our angle theta is changing as we go around the curve, these equations are only accurate for very short times. In practice, this means taking a small time step, figuring out the new values, then taking another small time step until you have moved for your full time. In this session, we've explored how we can model a robot's motion for a simple differential drive wheeled or tracked robot. We have derived the equations for determining our position and orientation based on the commanded wheel speeds. Now our robot can determine where it will end up before it has even started to move. Get your pencils ready for this week's challenge questions. This week's challenge questions are: imagine you have a robot that is 50 centimeters wide with a 10 centimeter radius wheels. The robot starts out at 0, 0 with an initial orientation of pi over 4. If the robot drives both wheels at a constant speed of 1 radian per second for 10 seconds, what is the robot's final position and orientation? Again, if the robot drives both wheels at a constant speed of 1 radian per second for 10 seconds, what is the robot's final position and orientation? Now, what if the robot runs the right wheel at 1 radian per second and the left wheel at 1.5 radians per second? What is the robot's orientation after 1 second of motion? Again, if the robot runs the right wheel at 1 radian per second and the left wheel at 1.5 radians per second, what is the robot's orientation after 1 second of motion? I'm John the Robot Doctor. See you next time.
Hey robot, that's not a circle.
You can find these video lessons online at WQED.org/therobotdoctor.